All right, here's the challenge problem we were talking about in class. So we have Miss Boudinot's wooden ball with a hole cut out of the center that I've modeled for us here. So you can see how it has a straight cut, it's like a cylinder down the center, and then it has a spherical surface. Now, from the side view, it has a certain height. Now, as it increases in radius into something that would approach Mr. Mahaffey's ball, the height has not changed, but the radius certainly has. So the height is constant. And the question was, well, which one of these has more wood? Which one has a greater volume? You can see how in this situation, the sphere, each side of that shape is thicker. And as you increase, they get thinner, but there's more length to it. And so there's these competing forces. So we wanted to identify how, which one is greater. So to do that, let's do it this way. I'm going to sketch the picture again. So we have here, and in class, I'm going to model which way we did it. We did it as a surface of revolution, where on our axes we had, it kind of looks like this. I draw it not quite in perspective. I could do it a little bit better. And we named some values here. So we said in class that it had a given height. For my purposes here, I might call this 2h and just say it goes up to height h and down to height negative h, just so we don't have to do halves. For all these situations, we had the original radius of my sphere, R1, capital R1. And then we had the inner radius of that cut. So I'll use maybe yellow there. So big R1 was determined by Miss Boudinot and Mr. Mahaffey, by how big they wanted their sphere to be. And then the height was set, and that really determined how big little r1 needed to be. I'm just going to note something here that we could sort of see because of the Pythagorean theorems always coming back, is that in this picture, it's pretty clear to see that h is right here. So that h squared would really be r1 squared minus r1 squared. Now for Mr. Mahaffey's sphere, it was bigger and all the calculations would be the same except that r2 would replace r1 for both the capital and the minuscule. So we can sort of reference that over here, that in any ball that we're doing, this is really the relationship that we're determining. All right, so now we can set up the integral. I'm going to do it first with the shell method, which is a little bit different than we did in class. But the shell method involves taking vertical slices here. Now let's recognize that this shape, the shape of that circular arc, well, the whole circle, its equation would be, Pythagorean theorem again, x squared plus y squared equals big R1 squared in this case, or big R2 squared in another case. And so for the cylinder method, remember it's always sort of 2 pi r times the height of your cylinder. So for this case, 2 pi, the radius is the distance from the center out to that particular wedge, which has a dx direction for its short side. That distance to that black rectangle is just x, times the height, which it goes up to this value symmetrically and down to that value. For our purposes here, let's just note that that's the y value, which I could solve as y equals plus or minus root r1 squared minus x squared. And there's that distance up and that distance down, so it's going to double. So it's going to be, the height's going to be 2 of that root, r1 squared minus x squared. Great. And then the bounds are, well, what does the x vary from? X varies from R1 all the way out to capital R1. All right, now let's just solve this. This actually works out really nicely for us. We have to do a little bit of u substitution. Let u equal what's under that radical. Not the radical itself, excuse me. So r1 squared minus x squared. Then du will be negative 2x dx. Substituting that into my equation, I get this. I'm going to have the square root, what's under there is going to be replaced by u. This 2, this x, and this dx will turn into a du, but we're going to bring a negative along for the ride. I'll stick it out here. And then we have a 2 pi left over. Now notice this, that we have these bounds. Let's change these bounds. So r1, well, u is equal to this. If x was r1, u would be r1 squared minus r1 squared, which is, in fact, h squared. So stick that in there, h squared. And if x was equal to capital R1, so these bounds, it would be r1 squared minus r1 squared, which is just 0. So I'm going to pause there for a second and say, we could take this now. It's really nice to take, super easy to do. I'm going to go ahead and say we don't really have to, because my question was not what is the volume. We could solve it. I mean, we could do that. But the question was, which one is bigger? And at this point, notice that u is a dummy variable. It's going to go away after I take this integral. All that's left in my bounds are h and 0. There's no more r1s. There are no more r2s. And all these calculations, if I replace the 1s with 2s, I get the same thing. And so right now, we can already generalize and say, well, look, this equation, this integral, is not dependent on your choice of r1. It's not dependent upon your choice of this, the radius of the sphere. Because when you subject it to the restriction of a particular height, that determines little r1 and it washes out. So it could be done. This part of the video is intentionally left blank. Now let's look at what would have happened if we used the other method. So I'm just going to go ahead and give us a little bit of space here. Oops, I'm going to keep that. Oops, let's get rid of these things here. I suppose I could have paused the video, but hey, I'm suffering through it. You're just going to have to hang on there. What would happen if we chose the other direction? So this is what we did in class. So if we chose the direction going this way, then our integral was set up like so. We'd have a dy. This is now going to be washers. So it's going to be pi, r squared. So the something squared minus pi something squared. Now the inner radius is always little r. And for this given radius here, that height, it's going to be, sort of like this value, but solve for x instead. X equals root r1 squared minus y squared. And we're going to subtract off of that little r1. So it'd be root r1 squared minus y squared. That's under the root. I'm kind of squishing. I apologize. Minus r1 squared. And we saw that its values are going to go from y equals negative h up to y equals h. Let's do some solving here. I'm going to pull out the pi. I'm just going to leave these alone for a moment. Let's FOIL that. So we end up with r1 squared minus y1 squared minus 2 times little r1 Oh, I apologize. There should not be a squared on the inside of that. That's coming along now. Times root r1 squared minus y squared minus little r1 squared. But it minus times minus gets a plus minus r1 squared. All right, dy. Good. Some of these things cancel. Kaboom, kaboom. And then we're left over here with, I'm just going to copy it down what we have, negative h to h, r1 squared minus y, did I call it y? What? My gosh, I'm in a rush because these videos cut off. Minus y squared minus 2r1 root capital R1 squared minus y squared dy. Good, zooming out here. Now this is one reason why it's nice to have two methods for the surfaces of revolution. Let's see what happens with this. Now I could try to do u substitution, but it's going to get really gnarly. It's possible, but we'll get really gnarly because if I use u equals the likely candidate is r1 squared minus y squared, then when the du comes out, I'm going to get negative 2y dy. That's fine for this, right? Because that would just turn into u. And this would turn into sort of like square root of u. But I'm looking at the dy. I need another y multiplied by it, and I just don't have that. Remember with the last method, we got an x on the outside, so that allowed us to do u substitution. I can't do that nice, straightforward u substitution here. And so I'm not saying it's impossible, but what you would do in a situation like this is you would say, well, why don't we look in the book and see what my table allows us to do? Because we could manage it. It's not impossible. But you'll see that if I just take this integral, I have my first value squared times, let's just take the integral. First value, r1 squared times y, minus y cubed over 3. And this whole thing, right, you're going to hate this. I look at my table and I say, oh, something of this form, where it's the square root of a constant squared minus my variable squared would be, I'm going to use some parentheses here, the variable over 2, copy the thing down, plus the variable squared over 2, inverse sine of y over that variable, the value r1, and we'd plug in negative h to h. Kind of gnarly, right? Let's see what that would really look like. Now, I could say we're done. We already did this, right? But this is, hey, if you're here for the ride, let's see what we get. So the pi's multiplying everything. So we're just kind of forgetting about that for a minute. And we say the pi's coming along. I'd have r1 squared h minus h cubed over 3 minus 2r1 h over 2 root r1 squared minus h squared plus r1 squared over this thing, to sine inverse of h over r1. So that's the first thing, and then we subtract off of that, plugging in the negative h. And I'm almost out of time, but let's pay attention to what sorts of things are going to cancel. I just pause the video to write that down with the negatives in there. And notice every single thing up here is an odd function. And so the answer is basically nothing's going to cancel. It's just going to double the first value. And so the project here would be to show why this gives me the same value no matter what R1 is. And so what you might try to do is say how maybe this R1 and this R1 and H all have relations, and we work them out. I'm out of time for this video, but think about how that could be the case.